Simon. I'm with the Gold team. And my teammates are Jason, Jared, and Jared. And we did voltage system. And I think we got the cream of the crop. We got the easiest portion of ours was steady state. Anyway, this was our system, a controller that went to a variable input generated to the motor generator, then to a sensor that was then sent back to our computer. And you see our input function, system, outputs, our voltage. Our voltage range was 70 to 95 volts for our system. This is our generator and motor downstairs, and they sent a load to the lights, as we've seen a few times. This is the light up. This is our steady state operating curve. This is the first part of our experiment we did a few weeks ago. You can see 83% input. We have a 70% steady state output. And this is our steady state operating curve data before. We broke up our I'm sorry, we haven't done that yet. This was for input at 85, 87, all the way down to 95. And this is our output for each portion. Activation, see, 2 times. It's pretty close. For our system. It was also a very responsive system. You can see our steady state operating curve is very smooth for our percent input. Didn't vary very much at all. Unlike some of the other systems you've seen, actually two exactly before this. Calculated our gain on our dead time, all that from our graph in the step response experiment. For a 2% step up. We broke up into our system into 4 sections, and this was one of the sections because there was 4 of us in our group. And here we calculated our delta C. You can see over delta M gives some gain. Gain is about 1.95 in that step response experiment for this. Again, another example. This is for dead time. We calculated dead time, of course, by just taking the smoothest graph we could, and from the initial point to that point, we came out to about 0.07 seconds in this experiment here. We averaged all that data, and then here's another one. Clarity. We averaged all this data, and we have here our gain, and for the step up, it was a little higher than it was for our step down. And it's the same thing for our dead time, and our taps. We're simply different. This is our plus or minus. Did vary pretty significant amount because I think where we're going with such a small region, we divided our sections, our 90 or 83 to 95%. We had to divide it into 4 sections, so it's a little noisy. Now, I put this in terms of what we did in our Excel for our modeling. Describe this all in terms of what we did in Excel. Red represents, of course, all our fixed variables. These are just the inputs that we didn't change to fit our model, to the curve. And black represents all the things we did change. And the way we do this in Excel, of course, was with an if function, it basically says that if time is less than the point where we did the step, it's going to be 0, plus the input baseline, which is 94% in this case, and for all values of t between 0 to 30 seconds. And that creates this little yellow line here, you see. the input line. That's how we created that. And of course, for the output function, for the match the model curve, we did time, dead time. If time plus the point at which we did step plus the dead time was less than time, the initial that time there, then it would just output 0 plus the output baseline. And that we had to modify to get this blue graph to align with that red graph. And that just simply represents that 91.55 volts represents the point at which it's the output at steady state output at 94% input. And in order to match our data to the curve, of course, if it was greater than that point, then the graph started. And of course, we have to subtract that time from the initial time. Otherwise, it would create a really big time, and the graph wouldn't look right. It would just look like that blue line would just go across the screen because it'd be a very small change at that point. We're going to adjust for that there. And our tau on the bottom controls how wide the graph gets. So we had to adjust that to get it to match up. So we modified that, and also A, of course, changes in this case, our A was -2. That gives it whether it's going to be positive or negative. Our steps down match much better than our step ups. This is our at 92%, one of our regions here. For step up, for 2% step up, this was our input, and this is our output. You see, it matches pretty closely. A little bit of noise in there, but it's not a big deal. Now, it's interesting because this is actually one of my graphs, and in order to make it match as much as possible, I set my dead time to 0, which is probably a bad idea because we're supposed to have some dead time. And it kind of skewed our data. I was going to change it, but I figured, I'll put it to 5/4, so I didn't bother. But again, that points out how subjective a lot of this stuff is. We're trying to model everything, but pretty much all of our values in the end are very subjective because they're based on perceptions that we have. So you can see here for the step up at 83%, it fits quite well. Step down at 5%, it fits quite well with relative uncertainty. Pretty close there. Some of these fits, of course, there was no uncertainty because it was all the same. Just use the same function and transferred well. So all the way across from 83 to 95 or 94, ups and downs. And, so they're pretty close. Not very much interesting stuff going on there. For a dead time, that varied a lot. And again,